Today I'm going to go through the topic 1, which is about atomic structure. This session will include atom, elements, compounds. Number 2, chemical and balanced equations. Number 3, mixtures and separating techniques. Number 4, the history of atoms. Number 5, electron structure. So we're going to start with atoms. All substances are made up of atoms. An atom is the smallest part of an element that can exist. Atoms contain protons, neutrons and electrons. This can be easily remembered as PEN, so P protons, E electrons and neutrons. The picture down below demonstrates the atomic structure, which basically means the structure of an atom. So, inside the atom you have the nucleus. The nucleus contains protons and neutrons. Protons are positively charged and neutrons have a charge of 0. This makes the overall charge of the nucleus positive. Protons and neutrons each have a mass of 1, so this basically means that protons and neutrons are quite heavy. Surrounding the nucleus, you have electrons, which are represented as yellow circles on this diagram, and they are moving around the nucleus in electron shells, which is represented as the blue circle line. Electrons are negatively charged and they are very tiny compared to a nucleus, so the mass is usually represented as 1 divided by 2000 and often taken as 0. So this table summarizes what was discussed on the previous slide. So it just shows the mass as well as the charge of a proton, electron and a neutron. This must be learnt for the exam. Atoms have an overall charge of 0, and this is because an atom will always have the same number of protons as well as the same number of electrons. Now, protons are positively charged, electrons are negatively charged, therefore they will cancel each other out. For example, if it has 6 protons, it will have 6 electrons and give an overall charge of 0. Additional points that are included on the syllabus that needs to be known for the exam is that atoms have a radius of about 0.1 nanometers, which can also be represented in meters, which is shown in the brackets, and the nucleus is less than 1 divided by 10,000, which is also represented in meters in brackets. So the next slide talks about the elements. We're going to look at the definition first, and the definition must be understood as well as memorized because there are key points that needs to be included in the answer if this question was to be asked in an exam. So an element is a pure substance made up of atoms joined together, but remember it's made up of one type of atom only. Where it mentions pure substance, this means it can't be broken down into a simpler substance by physical or chemical means. Some of the examples of elements are oxygen, iron, hydrogen, magnesium, copper, and these are the symbols for those elements, which can be found on the periodic table. So the next part shows the link between the idea of atoms and elements to give you a better understanding of how elements are formed. In this diagram, the small green circles represent the copper atoms, which are joined together to form a copper element. Atoms of the same element will have the same number of protons, and atoms of different elements will have different number of protons. For example, all the atoms of sodium element will have 11 protons, whereas for magnesium, they will have 12 protons. So it's the number of protons that determines the type of atom. Each element on the periodic table will have an atomic number and a mass number. Now, mass number is sometimes referred to as relative atomic mass, which is shown on the periodic table. Atomic number is the number of protons, which is also equal to the number of electrons. Mass number is the total number of protons and neutrons in an atom. So let's look at the diagram with the sodium from a periodic table. So the number at the top represents the mass number, and the number at the bottom represents the atomic number. As we said from the definition, the atomic number is the number of protons as well as electrons, which means the protons for sodium is 11 and the electrons for sodium is 11. Mass number is 23, and that's the total number of protons and neutrons. So from this, the number of neutrons can be worked out, because if mass number includes the protons and neutrons and the atomic number is just the number of protons, if you do mass number take away atomic number, it will give you the number of neutrons. In this case, the number of neutrons for sodium is 12. So atoms of each element on a periodic table are represented by chemical symbols. So rather than writing sodium as a full word, it can be shortened to Na. So for oxygen, it's just O. So in the previous slides, we spoke about the definition of atoms, the definition of elements, and how atoms can form the elements. And now we're going to have a look at how we can find the atoms and elements in a given compound, for example. So first one, sulfuric acid. It's represented as H2SO4. So if we're looking at how many atoms sulfuric acid has, it's got 2 atoms of hydrogen, it's got 1 atom of sulfur, and it's got 4 atoms of oxygen, which means the total number of atoms sulfuric acid has is 7. And the number of elements sulfuric acid has is 3, because there's hydrogen, there's sulfur, and oxygen. So it's just looking at the elements that can be found on a periodic table. Example number 2, iron sulfide. It's FeSO3. So the number of atoms is the total of 1 iron atom, 1 sulfur atom, 3 oxygen atoms. And the elements that's included here is iron, which is Fe, sulfur, which is S, and oxygen, which is O. And example number 3 is copper sulfate. So looking at CuSO4. So the number of atoms will be 1 copper atom, 1 sulfur atom, 4 oxygen atoms. And the elements is 3 because it's copper, sulfur, and oxygen. The next part of this slide explains the definition of isotopes, which is also required in the syllabus. So isotopes are different forms of the same element, which have the same number of protons but different number of neutrons. So this means isotopes have the same atomic number but different mass numbers. Let's look at an example. We have carbon here. There's carbon 12, carbon 13, carbon 14. If you have a look, the atomic numbers are all the same. It's 6, 6, and 6. However, the mass numbers are different. Therefore, the number of neutrons will also be different. So here we're looking at the compounds. Again, definition is very important that you understand as well as memorize for your exam, as these key points have come from the mark scheme. So the definition of compounds is when 2 or more elements chemically bond and cannot be easily separated. This is known as a compound. To make these bonds, atoms either have to give, take away, or share electrons. When making these bonds, the electrons are only involved and the nucleus is unaffected. The compound that is formed is represented as a formula, which uses the symbols of the atoms from which they are formed. Just as elements are represented by symbols, so for example, if it's a sodium element, it's represented as Na. Compounds are also represented as formulas. So for example, carbon dioxide or sulfuric acid, which is H2SO4. Compounds which are formed from metals and non-metals consists ions. So when metals lose electrons, they form positive ions, and non-metal atoms usually gain electrons and they form negative ions. This will be covered in more detail when we are talking about bondings as one of the topics. Now, compounds formed from non-metals, which are like molecules, each atoms share an electron with another atom. Usually it's difficult to separate compounds into elements, and if so, chemical reaction will be needed, and this is usually represented as word equations. The green text is what's been highlighted by the examiners. So, Students should be able to use the names and symbols of the first 20 elements, elements in group 1 and 7, and other elements that's included in the specification. Students should also be able to name compounds from a given formula or a symbol equation. And finally, write word equations as well as balanced chemical equations for the given reactions. On this slide, I will be demonstrating how chemical equations can be written. It might not make much sense at start, but as we cover the other topics, it will become much more clearer. So chemical changes are shown using chemical equations. One way to show this is using word equations. For example, methane plus oxygen gives you carbon dioxide and water. So everything on the left-hand side are reactants and everything on the right-hand side are products formed. Another way to represent chemical equations is symbol equations, which uses symbols and formulas of the reactants and products. For example, magnesium will be represented as Mg, oxygen will be represented as O2, magnesium oxide will be represented as MgO. It might not make sense how magnesium oxide is represented as MgO, but you will have a better understanding when we cover the topics of ionic bonding. On the previous slide, you might have noticed that there are numbers in front of the symbols. This is what you call a balanced symbol equation. So on this slide, we're going to learn how to write balanced equations. So step 1, write the symbols on how they naturally exist for the word equation. So looking at magnesium plus oxygen gives you magnesium oxide. Magnesium naturally exists as Mg and oxygen exists as O2, not O, and magnesium oxide is MgO. Step 2, check the number of atoms for each element on either side. They must always be the same number of atoms on both sides. So example, looking at the reactant sides, there's 1 magnesium. On the product side, there's 1 magnesium, which means that they both have the same number of atoms on either side. However, looking at the number of atoms of oxygen on the reactant side is 2, and on the product side is 1. And this is where we have to balance the equation so that the number of atoms on either side are equal. This follows on to step 3, where you balance the equation by putting numbers only in front of the element or compound, and you can't change the formulas. So for example, if oxygen naturally exists as O2, you can't change it to O3. So relating it back to our example, where the oxygen on the product side is unbalanced, you can't change the O to O2, and instead you put the 2 in front of the MgO. This will now give you 2 oxygen atoms, however it will also give you 2 magnesium atoms on the product side. And this leads to step 4, where you balance the magnesium on the reactant side by placing a 2 in front of magnesium. So now you end up with 2 magnesium atoms on the reactants and product side, as well as 2 oxygen atoms on the reactants and product side. So this slide looks at mixtures. So the definition for mixtures is when 2 or more elements or compounds are not chemically bonded and the chemical properties of each substance in the mixture are unchanged. Mixtures can easily be separated using a physical method. So the physical method is one that doesn't involve a chemical reaction, so it doesn't form new substances. For example, filtration, crystallization, simple distillation, fractional distillation, and chromatography. So for this section, students should be able to describe, explain, and give examples of specified processes of separation, and also suggest suitable separation and purification techniques for mixtures when given appropriate information. We're going to now look at each separation techniques in further detail. So we're going to cover paper chromatography, filtration, evaporation, crystallization, simple distillation, and fractional distillation will be covered in another topic. Each of these separation techniques are practicals and students must learn the step-by-step procedures, as in an exam you could be asked to describe how to carry out one of these separation techniques. The first one we're going to look at is paper chromatography, and this is a technique that can be used to separate different dyes in an ink. So step 1, draw a line near the bottom of the sheet of the filter paper. And to draw the line, you have to use a pencil. This is because a pencil is insoluble and won't dissolve in the solvent. Step 2. Add a spot of ink to the line and place the sheet in a beaker of solvent. Example, water is a solvent, but you also need to make sure that the ink isn't touching the solvent. Not all compounds dissolve in water, therefore ethanol can also be used as a solvent. Step 3. Place a lid on top to stop the solvent evaporating. Step 4. The solvent seeps up the paper, carrying the ink. Step 5. Each different dye in the ink will move up at different rates, so the dyes will separate out. One spot per dye in the ink. If any dyes are insoluble, it will stay at the baseline. The baseline is the line we drew in step 1. Step 6. When solvent reaches the top of the paper, take the paper out of the beaker and leave it to dry. The end result is a pattern of spots called chromatogram. The second separation technique is filtration. So filtration separates insoluble solids from liquids or solutions. Insoluble solids is basically a solid that cannot be dissolved. Let's look at the steps of how to perform filtration. Step 1, place a beaker on the table. Step 2, place a filter paper in a funnel folded into a cone shape. Step 3, pour the liquid reaction mixture and the filter paper will collect the solid impurities and the solvent will be collected in the beaker. This is demonstrated on the diagrams below. So on the previous slide, we had a look at how we can separate insoluble solids from solutions. So now we're going to focus on how we can separate soluble solids from solutions. And there are 2 ways. The first one is evaporation. Step 1. Pour the solution into an evaporating dish. Step 2. Slowly heat the solution. This can be done using a water bath or an electric heater. It doesn't require a Bunsen burner. The solvent will then evaporate and solution will get more concentrated. This will lead crystals to be formed. Step 3. Keep heating the dish until you are left with dry crystals. The reason why there are 2 ways that you can separate soluble solids from solutions is because evaporation can only work if the salt doesn't decompose when heated. Otherwise, crystallization needs to be used. So crystallization is the next separation technique. Step 1. Pour the solution into an evaporating dish and gently heat the solution. Some of the solvent will evaporate and solution will get more concentrated. Step 2. Once solvent has evaporated, crystals will form, and this is called the point of crystallization. Remove the dish from the heat and leave the solution aside to cool. Step 3. The salt should start to form crystals and become insoluble in the cold. Filter the crystals out of the solution and leave them in a warm place to dry. This slide is going to explain simple distillation. Now, simple distillation is used to separate out a liquid from a solution. So step 1, the solution is heated. The part of the solution that has the lowest boiling point will evaporate first. The vapour is then cooled, condensed, and collected into a beaker as shown in the diagram. The rest of the solution is left behind in the flask. So this can be used to separate pure water from seawater. The only problem with this separation technique is that you can only separate things with very different boiling points. If the temperature goes higher than the boiling point of the substance with the highest boiling point, then it will end up mixing. To separate liquids of very similar boiling points, you use a method called fractional distillation, which will be covered later on. This slide covers the history of the atoms, and these are a few main points that you need to know in regards to this section. So the first point is, before the discovery of an electron, atoms were thought to be tiny spheres that cannot be divided. The discovery of electrons led to the plum pudding model. This model suggested that the atom is a ball of positive charge with negative electrons embedded in it. The result from alpha particle scattering experiment led to the conclusion that the mass of an atom was concentrated at the centre, which is the nucleus, and that the nucleus was charged. This nuclear model then replaced the plum pudding model. Niels Bohr adapted the nuclear model by suggesting that electrons orbit the nucleus at specific distances. Later experiments led to the idea that the positive charge of any nucleus could be subdivided into smaller particles, each particle having the same amount of positive charge. The name protons was then given to these particles. The experimental work by James Chadwick provided evidence to show the existence of neutrons within the nucleus. The discovery of neutrons resulted in a model of the atom which was pretty much similar to the nuclear model. So this slide looks into the electron structure. So electrons occupy shells around the nucleus. The electron structure, also known as the electron configuration, can be shown as diagram as shown below, or as numbers. So looking at the diagram, this is the electron structure for a sodium atom. So you have the nucleus in the middle, and then you have the first shell, which is the inner shell close to the nucleus. Following that, you have the second shell and then the third shell. Electron configuration can also be represented as numbers. So what you do is you write how many electrons are on each shell. So again, for sodium, on the first shell it will be 2, and the second shell is 8, and then on the third shell is 1. Electron configuration has some rules. So number 1, electrons always occupy shells, which is also known as energy levels. This means that a shell must be full before filling in the next one. Number 2, the lowest energy levels are always filled first. These are the ones that are closest to the nucleus and also represented on the diagram above as the first shell. Number 3, only a certain number of electrons are allowed in each shell. So the first shell can only occupy 2 electrons. The second shell occupies 8 electrons and the third shell occupies 8 electrons. So referring back to the diagram, looking at the sodium atom, we know that the number of electrons on a sodium atom is 11. So you draw the first shell, which can only occupy 2 electrons, which then means that you have 9 electrons left. And then you draw the second shell, which can fill in maximum of 8 electrons, which means there's 1 left over. So you draw the third shell, and that electron sits on that outer third shell. Atoms are much happier when they have a full outer shell. In most atoms, the outer shell is not full, and this makes them want to react to fill it. So usually, the third outer shell can hold a maximum of 8 electrons. And referring back to the diagram above of the electron configuration of a sodium atom, it only has 1 electron on its outer shell, which makes it more reactive. To summarize this session, you should be able to define atoms, elements, compound and mixtures, and to also give examples of elements and compounds. Then you should also be able to write word equations as well as symbol balanced equations. And again, balanced equations will come within practice as we cover the rest of the topics. And then be able to describe the procedure of performing each separating techniques, and briefly understanding the history of atoms, and finally the electron structure. That's it for today. Thank you for listening.